Okay, so today we're going to look at part 2. Now if you think back all the way to part 1, what I focused on part 1 was the whole idea of the computer's brain being this thing called the CPU. And do you remember what the two parts it was broken up into were? ALU, yeah. And CU, yeah. Do you remember what those stood for? Not algorithmic. Arithmetic, yeah. So this thing does the math part. It does the adding. And then what is CU? Control unit, yeah. And then there was one other piece to a CPU that's essentially just memory. Right? So it's like this is the spot where it keeps track of the instructions and where it keeps track of the results. This is also sometimes called the immediate access store or just storage. But it's essentially memory. Okay? Now, do you remember the cycle? That was also something, so also called the machine instruction cycle. And it could be as few as 2 steps. Do you remember them? Anyone? I'll give you the second one if you're going to do 2 steps. It was decode. Fetch, yeah, fetch. So you fetch an instruction, you decode it, okay? And then execute, right, execute. And then sometimes this is called the fetch decode, sometimes it's called the fetch decode execute, and sometimes it's called the fetch decode execute store cycle. That basically is just what the computer does when it cycles through all your instructions. So as you feed it code, it sits on the memory, the control unit grabs it, runs through the cycle, possibly has the ALU do some math with it, it will, and then comes out with an answer, so like 2 plus 2 equals, puts the 4 on there, etc. But what I'm going to show you today is this piece of memory here is actually connected to a larger piece of memory in the whole computer, okay? So we're going to focus on memory today. But good, you got everything that we did in part 1 months ago. So that makes me really happy. All right. Come on, work. Work, damn you. Okay, so let's take a look specifically at what the IB says about this. It's just one slide today. I'm going to show you about this. Okay, so here's what you need to know. You need to describe primary memory, okay? Distinguish between random access memory and read-only memory and their use in primary memory. Explain the use of cache memory. Students should be able to explain the effect of cache memory in speeding up the system as well as being able to explain how it's used. And then finally, identify the need for persistent storage. Persistent storage is needed to store data in a non-volatile device during and after the running of a program. So we're going to make sure you guys know those terms, okay? There's even a couple links here to other things, including theory of knowledge, if you were interested what that means. But let's just focus on what I mean by this. So basically, let's talk about the difference between a primary memory and a secondary memory, okay? Primary is your main memory. It stores your instructions and the data in binary, okay? The control unit deals with the instructions, and the arithmetic and logic unit handles the calculations and the comparisons. These data and these instructions are moved around inside the CPU by buses. Remember, buses is just a fancy word for wiring, right? It's the way to transfer the data around. So inside of the storage area or the memory area, also known as the immediate access store, are 2 types of memory, RAM and ROM, okay? Now, ROM has this funny, RAM is a kind of a strange acronym. It stands for Random Access Memory, which really isn't describing it at all, okay? There's nothing random about it. Why it comes up with that name is beyond me a little bit. It's definitely memory, but it's basically reusable memory that's used by the computer all the time. Think of it like a piece of scrap paper that you're using. You're constantly writing to it and then erasing it, and then writing to it and then erasing to it. That's what RAM is, okay? Whereas ROM, which actually does make a little more sense, stands for read-only memory. So this is memory that you can't write to it, but you can read from it, but only read from it. So this is permanent instructions. So this would be things on your computer like how to start up, or important information about like the manufacturer of that computer, etc. It is stuff that is basically burnt right into the computer's hardware. So this would be important in memory that you can't change, okay? When the software, the programs, the data on your computer are not stored in RAM, then they're moved to other storage devices that can store things as well. Like, for example, a hard drive. A hard drive is permanent. Or a USB drive. Or even older devices like CD-ROMs or DVD-ROMs or even floppy disks back in the day. Those types of storage devices are permanent, but they're not RAM. They're going to be stored on there for a long time. Okay? And those are essentially connected to the CPU. Okay? So somewhere outside of memory would be places you can store data permanently. Okay? Like a hard drive. Okay? So the hard drive would be the simplest example of that. It could also be a USB drive. Okay? This type of storage, okay, is called persistent storage. Now, if you think of that word persistent outside of the context of computer science, it'll start to make sense. It's something that's persistent is always around, right? It's just constantly around. It's bothering you all the time. Persistent storage is permanent storage, okay? Whereas RAM, okay, and the storage here on the CPU, and I'm putting RAM here because RAM isn't actually on the CPU. We'll talk about that in a minute, is not permanent. It is constantly being written and written to, read, write to all the time. As well, it requires electricity to work. So if you pull the plug on your computer, anything you had stored in RAM is gone. It's wiped out. Okay? So this is not persistent storage. So other words to describe this, and we actually talked about this back when we did files as a programming unit, you may recall, was known as volatile storage. And what was this one? Non-volatile, right. Non-volatile. Volatile, again, means that it could get destroyed, right? Like a volatile chemical is something you watch out for. It's dangerous. So this memory, you know, is dangerous. It could wipe out. But as soon as you store it on something like this, it's not volatile anymore. It's persistently going to be there. And again, I just mentioned those words because they show up in the curriculum. If we jump back again to the curriculum a little bit, and I worry that it could show up in an exam question and it'd be like, what does that mean, right? Distinguish between random access and read-only in their use in primary memory, right? So there's the word primary memory. Persistent storage being used in the curriculum right here, okay? Now other words we're going to look at, oh, here, data in a non-volatile device. So there's those words again. And the next one we're going to look at is this word cache, right? Like, what does that mean? Okay. So primary memory, RAM, is that main piece of memory that you put inside a computer that is used by all your software to do calculations, okay? It is volatile memory because it's reliant on the computer being on. Like a chalkboard, it's constantly being written and erased. It's basically just switches, though. It's basically just silicon switches that flip on and off. And we talked, I think, a little bit about that last time, how these little on-off switches essentially work at that microscopic level. But that's all they are, is just these little, essentially ones and zeros switching on and off. Computers come with different amounts of RAM, and this is actually something you can upgrade in computers, especially desktop computers, but also laptop computers, and even tablets to some extent. Now, modern hardware has made this more or less difficult depending. Now, I know you guys who took electronics with Mr. Yak have probably seen this. You've probably even seen the slots where RAM goes. Back in the 90s when I was working with computers, this was by far the easiest upgrade you could make to a computer, was just put another, basically doubling the RAM meant doubling the speed of your computer. The more RAM you have, the faster your software could run, because now it had a lot more memory that it could access when it just needed to do what it needed to do. But eventually, that runs out, okay? Your primary memory even starts to run out. So if you think about this being the memory that's right on the chip. Now this, by the way, is called cache memory, okay? Cache memory is right on the CPU, okay? Then when you move outside of cache, you get to RAM. Okay? So I'm not going to draw too much, but let's go here again. So here's our CPU, and on there is our cache memory. Okay? Then connected to that is our RAM memory. Okay? Now, if you were actually to look inside a computer, the RAM is actually separate from the CPU. They're separate pieces of hardware. They're very close together, though, okay, in terms of the actual physical space. And even if you open up a laptop, they're physically close. And that's because they don't want the actual data to travel very far to get here, because it's limited by something, the speed of light. The electricity can only go at the speed of light, and it wants it to get there as fast as possible. But eventually, depending on the complexity of your program, this might fill up, and this might fill up. These two things are technically defined as primary storage or primary memory. Okay? The cache obviously is more primary, but then RAM itself is also primary memory. So whatever software you're running, you want it to be running in here. The more it's running in here, the better it's going to run. But eventually, when that fills up, it's got to download somewhere. There's, like, you have some instruction, or like say it's a complex game, it's waiting for a bunch of instructions to take place. It has to then go to secondary memory. Okay? And what secondary memory is some of that persistent storage. It temporarily writes some information on the hard drive. And that would be where it can get at that data later. We want to minimize this as much as possible because secondary memory in persistent devices are slow in comparison. Yeah, that's another piece. So secondary memory would be things like a hard drive. And then something that's not quite, it's hard to put it into a category, but what Jesse mentioned was VRAM. The V in VRAM stands for video. Okay? VRAM often sits on your video card. Well, that's where it does sit, not often. That's where it sits. And what that is it's memory built right into the video card specifically for running video instructions. Now, in a way, that's secondary memory because it's not part of RAM or part of cache. But what the CPU is now, is CPUs are smarter. They can send some of the instructions there that are specific to, say, video and like things like that. So VRAM, video RAM, is just another piece of RAM. That's why if you buy a super expensive video card, you can run much more powerful video on your computer because it's giving some of that instruction set to VRAM so it doesn't have to deal with it in its system, right? It's like, you take care of that. You take care of yourself there, VRAM. And so that's what it does. So that's a good point. Okay? Now, in the future, other types of hardware might also require that. You'd think, well, maybe they also do one for audio. Well, generally, the audio doesn't take up the amount of memory that, say, a video device does. So yeah, that's more memory intensive in that regard. Okay? Okay. So secondary memory would be persistent storage, peripheral devices like hard drives, disk drives. Okay? These also sometimes are called backing stores, okay? Although that term isn't really used that much anymore, just like a print shop CD is not used very much anymore, but nonetheless. So you have to wait as the computer loads up all of its instructions from various pieces of memory. The more RAM you have, the less you have to go to secondary memory. That makes your computer overall work better. So on the system's memory, on the system's CPU, onboard memory or cache is the best place. So the more memory you have right on the CPU, the more expensive the chip is that you buy, right? I mean, chips are sold based on the speed they can execute, but also based on the amount of memory built into the chip, okay? Which is maybe why sometimes if you ever go and look up specs of a computer, you'd see, well, this computer and this computer seem to be running at the same speed, but why is this chip more expensive, even though they run at the same speed? Well, part of it could be because it has more onboard memory, okay? And most likely that's why. But then once that's full, it goes to RAM. And once RAM's full, then it goes to secondary memory or some sort of hard drive. Ultimately, we'd want to run all our software right here, but because of the complexity of our software, it then starts going here, and even more complex software starts going here. And managing that memory is what we want to do as programmers, is just knowing that that occurs, we want to kind of optimize memory usage as much as we can as programmers. Okay, I believe I just said all that, okay? Okay, so having a lot of onboard memory would be the best, then having the most amount of RAM would be second best after that. Okay, now other than that, some other terms that you could be familiar with. The term SIM just stands for single inline memory module. That's just basically one of the pieces of RAM that you'd use, okay? They are put into your computer in slots. Often when you buy a new computer, it will come with an empty slot or two that you will have to use if you want to upgrade the memory. If it's not coming with empty slots, then the only way to upgrade your RAM is to pull out the RAM you have and put in new RAM, which is kind of a waste, right? Now you've got this RAM that you're not using. Back in the 90s and the early 2000s, when I used to do a lot more hardware type stuff, there was also limitations on that. Sometimes you had to put it in pairs, right? The RAM had to always be put in pairs and stuff like that. It depends now. There's no one answer to that stuff, nor should you need to worry about it at the IB level, okay? And then cache memory, okay, is really divided into two sections, cache being the most powerful section of RAM, okay? The main RAM and the cache memory. Cache is essentially also a word that it does generally mean the memory right on the CPU, but cache also is a very open-ended term. Cache often is used to describe just really expensive memory, okay? That just works better. So cache is sometimes used in that way. But generally, a cache is like the memory queue that's right next to the CPU, okay? It's the high-speed, expensive memory that's going to work the best at the shortest distance. And again, it can get more specific than that, and I've lost the memorization of all these terms myself, but there used to be things called pipeline burst cache and level 1, level 2 cache and stuff like that. In no way do you need to know that level of detail. You saw what you needed to know from the IB curriculum, okay? And then these are measured in byte values, right? From mega to giga to terabyte, etc. You guys kind of know that general idea of cache and memory being measured in amounts, in byte amounts. Okay, and then the video RAM, as I said. The video RAM is a piece of RAM built into the video card specifically for video production. And so, for example, a gaming PC would want to have a high VRAM on the video card. And by the way, when I say the word card, because it's so common, card is just a circuit board, okay? And generally the term is that these cards are expansion cards, right? They plug into the motherboard, and the board is just a circuit board. So if the motherboard is the main board on the computer, these cards are also called daughter boards because they plug into the motherboard. But basically they're just a circuit board. Okay, any question about memory? All right, the next piece I just wanted to touch on was operating systems, which manage memory. So I just want to bring this up. So an OS, or an operating system, is what manages the memory of your computer, but at the same time manages all kinds of stuff on your computer. So the software itself is managed. Basic functions of the computer, such as input-output, is essentially managed by the operating system, okay? But over the years, operating systems have expanded what they can do beyond just this basic functionality. So in the beginning, operating systems would just do that. Do any of you guys know an early operating system before, say, Microsoft Windows, what it was called? By Microsoft. Yeah, do you know what it stands for? I'll give you the S. It stands for system. And I'll give you the O. Operating. No. Disk, actually. D was disk. DOS stands for disk operating system. So all it did was it was a system for managing your disk, which was your hard drive or your floppy drive back then. It was just that, okay? But over the years, it's expanded, right? So now they give it fancy names like Windows and Mac, calls it Mac OS. And everybody like Linux and Unix, they give it fancy names like ice cream sandwich and stuff like that, and all kinds of fancy names like that. But that's what it was just a way to manage that stuff. So it knew the hardware was doing this, but it found a way to communicate the hardware with the users. And then over the years, this has become more like graphical. So they added graphical user interfaces to it. Whereas when I first learned about computers, it was in this system, right? It was in a DOS-based, just text-based system, and then the graphics were being built slowly on top of that. So now we don't even see that that's occurring, okay? Here's some throwbacks for you guys for operating systems. Unix was the predecessor to Linux, okay? VAX VMS, okay? OS2, which was put out by Intel, was thought to be a competitor for Windows 95 when Windows 95 came out. I actually remember going to a computer expo in 1994, and Intel had set up this huge booth to talk about OS2 and how it was going to wipe out Microsoft completely, etc. Here's some examples of them, right? This is like your classic Windows 95. Here's your classic Mac OS, a little bit older ones for sure. This would be a classic Unix OS. Now we call this Linux, and it's a lot prettier looking, but that's a classic Unix interface. And then this was OS2, and actually if you look at it, it looks a little bit slicker almost than some of the other ones at the time. Okay? Mac built its OS heavily on Unix background, right? So did Microsoft to some extent as well. But Microsoft liked to kind of do things on their own because Microsoft had all these partnerships with hardware companies, whereas Mac didn't. Mac didn't have to make partnerships with hardware companies because they were the hardware company that was making their own hardware. So they didn't have to worry about it, whereas Windows had to worry about partnering up with all kinds of different hardware systems. So did IBM, but they just didn't compete as well in that environment, okay? Now, outside of your personal computers, you can also think about things like mainframe computers. We talked briefly about this before, but mainframes are not personal computers. These are much larger computers that run off a terminal system that you see in things like military institutions and stuff, although even those are starting to move away from those now. So what we have here with mainframe are what are called multi-programming operating systems, or and then with microcomputers or PCs, we have multitasking operating systems, which you guys are good at. You've grown up in that world where you can open up an operating system and do several things at once. You don't have to do one thing at a time, okay? But we got to also think outside of computers per se. Sometimes as well, we run older systems in something called batch mode. Batch mode just meant when you gave it a job to do, it would do that job until it was done. And in order to then get to the next job, it would put the job on a stack. Now, I could say literally a stack, but you guys also know what a stack means in a programming sense. That it would just run through the job and then move to the next job on the stack, okay? Batch processing is now reserved for really important data transfer things, okay? Like banks that run payroll things and stuff like that, or large companies, that they can run batch processes overnight to get those jobs so that the whole system is focused on that one job. You might even think of that for like 3D environments where they have render farms of computers that just have to focus on rendering and they don't want to do anything else until that job's done. Then we have something called real-time processing. And it's literally exactly what it says. It means it'll operate in real time. Now, most of the time, that's not a big deal. Like if you were on Skype playing a game, checking your internet, and on email, and then you decided to launch Microsoft Word, it's not a big deal to wait for Word. But in some systems, it is a big deal. Like, for example, airline reservation systems. They don't want, if they have a flight that's going from, say, LA to New York, but is making a stop in Chicago, and all of a sudden they're in LA, and the lady at the ticket counter, I don't want to say lady, I don't want to be sexist, the person at the ticket counter decides to add someone to the flight in LA. Meanwhile, at the same time in Chicago, some other airline person is also adding someone to the flight that's stopping in Chicago. We can't have those two things happening at the same time if there's only one seat left on the flight. So in a real-time operating system, it has to be working in real time. So what these systems often do is they have systems in place that wait to make sure that that's all gone through the whole system before they allow anyone else onto the system. Banks would be like this as well. So you couldn't like have two ATM cards and you and your buddy are in different parts of the city on your phone and you're going to coordinate, and say you had only had $100 left in your account. And you were trying to coordinate it at the exact same moment in time. You were both at two ATMs trying to draw $100 out of your account so you get $200, right? It won't work because they use a real-time system that will ensure that that won't go on, okay? So that's a real-time operating system. Other examples where it's data critical, where you can't have a delay, can you think of one? A computer system where it's absolutely important that you get that data at the right time. Exactly right, healthcare. Right? In healthcare, if you're on a heart monitor, you want that to be real time. You don't want like it to have the spinning little wheel while you're, hey, is that guy dead? I don't know. We'll just wait for let's reboot and see if he's dead, right? No, you want that real time. Okay, so what does an OS do? Well, it allows you to even get on, right? So there's an amount of security built into most modern operating systems to determine, you guys can't just, some kid off the street can't just log into these machines. Keeping track of resources, so who gets memory, right? When is it important? Handling errors, input, output. Interrupts, you may remember we talked, is like when something important happens on a computer, it interrupts what else is going on. Sequencing the jobs, putting them in order. Security, creating user interfaces for interaction. Allocating resources, like determining who gets printers or who gets memory. Executing the software that we write, and managing the memory. Some of those kind of overlap in what they're talking about. Main memory is limited, so the operating system has to do a really good job at this. I mean, we hear about these companies like Microsoft putting out OSs, and we worry about the little details, like how pretty the start button's going to be, and whether I get. But to be honest, what they put most of their programming time into is to this stuff. This is what takes the time, is to actually manage all that stuff. That stuff is usually put on at the end as little pretty features for the consumers, right? Now, just to step back a sec again, when you run out of memory and you have to go to a peripheral, like a hard drive, there's different words that sometimes are used for that. Sometimes it's called virtual memory, which means you're storing memory on a hard drive. In Windows, they call this a swap file. You can actually see this in action on Windows. If you ever have like a Windows folder open, there's usually this little swap file, and you can watch its byte size go up and down depending on the program you're running. And if your computer's ever lagging, watch that swap file get huge because it's dumping a bunch of memory temporarily to the hard drive. Okay? Yeah, that's that. Last piece of the puzzle, utilities. Okay? This is extra stuff that's added onto OSs. Like things like copying files, deleting files, renaming files. The fact that we can do that was just an add-on feature that Windows gave you, okay? Other add-ons could include backups, formatting, like say you put in a CD to format it, or a new USB so you can use it. Maintaining your disk drive, archiving, compression, defragmentation. Some of these don't even mean anything to you guys anymore, I don't think. Do any of you know what defragmentation means? Any idea? Okay, so go ahead, Kyle. Keep talking as I draw. That's basically exactly right, okay? In the old IB curriculum, you actually had to learn a lot more detail about this, that the actual physical disks are made up of things called sectors and layers and stuff, but you don't need to worry about that. It's out of the new curriculum. But generally, when you think of a hard drive, and maybe just think of a CD, because it's the same idea. When you have, say you write an essay, and it's a Word file, DOC, and you go and hit save to save it. What's going to happen is, let's say at the same time you were writing this essay, you were also on Skype, listening to music, and was cruising the internet, and had Wikipedia open, otherwise you couldn't write the essay. So when the time you hit save, the essay is controlled on your system by what you may recall was called the file allocation table. That said, yeah, the FAT, yeah, not PH, but the FAT. And it allocated where that file's getting stored. So maybe part of your essay was stored here. And then part of it was stored over here. Part of it was stored over here. Okay? Because that hard drive was spinning, running all your software, at the time you saved it. So it didn't want to stop, it just kept going, and it put pieces of it all over there. So over here in the file allocation table, to get at your essay, it kept track of the 3 spots where it was stored. It remembered, oh, it's in sector whatever, layer, whatever, like it kept track of all the sections. So when you later want to go open up the essay, it knows exactly where to get all the pieces of it. Well, think of this over time. With all the stuff you're saving, your disk becomes a nightmare jumble mess. So in older systems, you'd have this what's called a fragmented disk, and it could run what's called defragmentation, which meant that it would go through your drive and your file allocation table, and it would erase this part and put it up here, and then this would be erased, and then it would find this piece and it would put it up here, and then this piece would be erased. And it would reconnect all your pieces so that when you later went to open up your essay, it went much faster because now it was all put together. So it's basically like organizing your sock drawer to put everything back together again. Yeah? I don't. Well, now, the thing is, defragmentation has become kind of a thing of the past because modern OSs do a better job at managing this stuff. And so the whole system now with file allocation and the way it manages, and even with solid states, is because it's not spinning like a normal hard drive was. So the exact reason why I'm not exactly sure, but I just know that they've gotten much better at doing this. But that was something that was very commonly done back when I was in the 90s. If your computer was running slow, or a friend of mine would say, can you speed up my computer? The first thing I would do is run a defrag on it. And then all of a sudden they'd be like, oh my God, it works so much faster. It's like, yeah. Because it just over time it built up kind of a junk, and you just basically clean it up, okay? Now as well, back in the 90s, we ran out of disk space quite often, so we used to do compression. We actually used to have to take files and compress them to smaller sizes for that to work. But then in order to use that file, you'd have to decompress it to use it again, okay? Now I'm going to talk about compression here in 1 second a little bit more, okay? Other things OSs do, backups, okay? This is not also that important anymore. It used to be a bigger deal. It will be if you work for a company. Companies run backups. That's more important. Formatting media, we talked about that, like a new USB. Archiving data. Okay, again, this is now moving to things like cloud storage devices and stuff like that. But it's the same general idea. Okay. Compression, like we just talked about. And this can be at a large scale or a much smaller scale. I mean, when you open up a JPEG file, you're dealing with a compressed file, right? A JPEG, by its nature, is a giant graphic that has been reduced in size so that it will be easier stored on memory devices. But then when you want to view that thing, it decompresses it, okay? Okay, so let me just wrap up, then I'll talk a little bit about compression just to wrap up today. Okay. So here's an example of how text compression would work. Okay? So let's say you had this sentence, the brown cow jumped over the lazy dog. Okay? Certain words, like the word the, can be represented by a single token. Rather than store THE, it could go, oh, I'm just going to store this token for the word the. And imagine this was an entire essay. It could just say, oh, you need the word the 70 times. So it says this token times 70, which would be a lot more memory intensive than storing the actual thing itself. But then it gets even more complicated. It starts looking at letter patterns like OW, ER, and ED, and it starts tokenizing those, okay? So compression has, and again, you don't need to know the details of it, but compression is kind of an interesting programmer type thing. That's what happens. So let's imagine I was going to draw a graphic, but at a microscopic level. So let's say I was going to draw an X, okay, on the screen. And that was the only graphic I was going to store. It was just a lowercase x. Well, at some level, let's say it was just a black X on a white background, okay? At some level, in order to draw that X, I would need a grid, like I'm drawing, and then I'd have to fill in some stuff to make the X like this. That one, and that one. Right? So that would make my X on the screen. But as you guys know, this would be like a matrix, right? So you'd think, okay, this is a 9 by 8 grid. And then I would start storing it. So in order to store the letter X on the computer, I would need to store a 9 by 8 matrix, and let's say it was black and white. So if it was black and white, I could store this one as a 1, and this one as a 0, right? Zeros, and then a 1, okay? If I had more complex colors other than black and white, each pixel, right, and you may remember the word pixel is short for picture. That's the word picture, and that part is for element. Picture element. So each little element of the picture would be a number, right? If I wanted to use 16 million colors, then there'd be 16 million possible numbers you could store at each spot. But with just a black and white, I could just store ones and zeros. Okay?
Please report to room 2E6.
So if you imagine this thing, if I finished filling it out, it would be mostly what? Mostly zeros, with some ones interspersed within it. So what a compression software would do is it would look for patterns of mostly, for example, zeros. And rather than store all those zeros, it would say, okay, you have a 1, and then you have 1, 2, 3, 4, 5, 6, 7. 7 times zeros, and then another 1. And then in the next line, you'd have a 0, a 1, and then like 6 times 0, and then a 1, and then a 0. Like, depending on the way the pattern works, it can store it more efficiently by compressing it. But then when you go to rebuild this image, it would go through this, and it would decompress the image, right? When it's not compressed, it's called essentially a raw image, or just a, for example, a format for a graphic would be the bitmap format, BMP, which is a raw image, okay? Whereas the JPEG is a compressed image. Okay. And it does this with text, and it does this with audio, and it does this with video. And programmers over the years have built these pieces of software that do this compression, okay? Viruses, I think we know what those are. You guys can program them now, okay? There are subtle ones like Trojan horses. There are virus checkers. There's all kinds of stuff to deal with viruses. Most operating systems have some of that built in now, so it can check with viruses. This was a big deal in the late 90s and the early 2000s. It's become still a deal. It's still a big deal, but less so on a personal level, more so on a like company level now. Okay. Where are we at here? Running out of time. So let me just jump back here for a second. Now, when you go and use something like a linker, this is where it actually runs software. The way operating systems run software is it loads it up and then executes it. But it also sometimes needs to link it to other libraries, depending on, and I mean, some of you guys, if you think about the games you guys wrote over the years, especially for your IAs, your code is linked to other code. So sometimes the execution of a program is linking it to several things at once, okay? Depends on what the way the CPU, the CU, and the ALU interprets that, okay? All right, and we are done. Let me just jump way back, though, for 1 second before we go any further. By the way, there is a little bit of bonus content for this. I'm not going to go through it today, but you can read. It's just stuff from the old curriculum that we're done with now at the new curriculum. But if I go back to just the fundamental part of the curriculum, let's just make sure we're there. Here we are. Let's review. Describe primary memory, distinguish between random access and read-only memory. Explain the use of cache memory to explain that cache memory speeds up the system. Identify the need for persistent storage is needed to store data in a non-volatile device during and after the execution running of a program. I hope that's clear to you guys now in general what that is. I don't think we'll have time today for an exam question because I can feel how